Welcome viewers to the second session of our course on machine design. This is part of Module 1. In first session of Module 1, we have discussed about the design process, the different steps that we have to use or follow for general design. And in this session, we will be introducing how to write design equation. And so we'll be starting with the basic concept of strength of material problems, as we have already undertaken this course on strength of material. So let us begin with a simple problem of a prismatic bar with subjected to some load F and deformation delta. Then the simplest problem that we have in strength of material is find maximum value of stress for given load and the dimension of the bar or a member. We use this formula for this finding out stress. In this case, the maximum value of stress is same if we calculate stress at any point. As we have already discussed, that stress is always calculated at a point. Whatever formula we write for stress, this will always be at a point. For axially loaded members, we assume that stress is same throughout the volume or throughout the member, so that is why everywhere it is maximum. Otherwise, in case of problem related with bending stress or twisting stress, we have to identify a point where the stresses are maximum. So we can find out the maximum value of stress using this simple expression. We get this is the type 1 problem, we can say, if we categorize the different types of problem that we solved in our strength of material course. This is type 1 problem, and most of the problems were related with this, that some load is given and the dimension of the member is given, and we have to find out the maximum value of stress, and sometimes we have to only find out value of stress at some specific point. The second type of problem is like this, that we have to find out the required cross section of the member for given load, and maximum permissible stress is given, and this stress we also call it as design stress. So this is the second type problem that we have done. To solve this, we can write down the same equation in different form, and we have simply changed this, arranged in a specific manner, so that we have the right hand side term, that is design stress, and left hand side term, which is the induced value of stress. So F over B square is nothing but it is F over A, that is sigma. So this value is induced stress, this is the induced stress, and this is design stress, and F is external load. We use this concept and find out value of B, that is in this case 10 mm. So comparing this equation and this equation, we can now see for design, because in design we have to evaluate some dimensions. So in design type of problem, we have to use this form of our basic stress analysis equation, where the left hand side is the maximum value of stress, induced stress, and right hand side it is the allowable value of stress, permissible value of stress, limiting value of stress, or design stress. So it means that we can write our design equation in this form. On the left hand side, it is maximum induced stress at any point, so this point we have to identify in a loaded machine member, and it should be equal to less than equal to design stress. And for optimum use, we have to convert this inequality symbol to the equal symbol. The other type of problem that we come across in strength of material was related with this: find required cross section of the member if maximum elongation is delta maximum, and it is given as 0.001 or anything. So for this problem, we have to use another form of this equation, that we have to use the basic stress strain relationship, Hooke's law, and then we can find out this. So in this case, we again use something which is on the left hand side, we have the induced maximum induced deformation. On the left hand side, it is the maximum allowable. So we can find out the dimension in this form. So this particular case, we can write down design equation like this, that maximum deformation, that is, that may be axial or twisting or sometime even slope or deflection in case of bending at any point in the loaded machine member should be less than equal to this, and for the optimum design we have to take equal sign, and this is maximum permissible value. So we have now come up with two different equation. One is this, another is this, and this equation we call it as we are using design equation on the basis of strength. So we are designing a component on strength, and here we are designing component on rigidity. Now if we see the right hand side and the left hand side, we find that the right hand side equation, we get design stress, and design stress is obtained using this formula that is very popular in machine design. We will be discussing this slightly more in our later lecture in module 2, and this design stress is obtained by dividing strength by factor of safety. We should also note that the design equations are to be developed at a point, because we are always calculating stress at a point, number one, and even deformation at a particular point. So we are writing design equations at a particular point, and these design equations are for static load. For dynamic load, basic uh, structure of the design equation will remain same, but something that what is the difference, that we'll be discussing later on when we discuss the fluctuating stresses in the later modules. So now let us see how to get the left hand side of the problem. Left hand side was calculating maximum induced stress, and maximum induced stress should be at a point that we are emphasizing time and again that stress is always calculated at a point. So for example, if we take this case where a member, this is a member, it is subjected to different loads like this, and if we have to design this particular member, we have to find out where the stresses are maximum. Or let us say that I want to find out stress at this particular point. So to find out stress at this particular point, I have to find out what is the value of load. It may be F, it may be M, that is bending moment, it may be twisting moment, because of all these loads. So it means that to find out stress at this particular point, I need to find out the value of load at this particular point. And there is no direct load acting at this particular point. So load which are acting at away from these point, we have to find out what is the effect of all these load at point A. So we have to find out the effect of all these loads, that is 500 Newton load at point D, and likewise and so on. Means we have to find out the effect of loads acting at different points at point A. So that is unless until we are able to find out the effect of loads at point A, it is not possible to write the stress. It is not possible to calculate stress at this particular point A, and if we are not able to calculate stress at this particular point A, we are not able to write down the design equation properly. So now let us see another example. If this is the example where these two members are connected through bolt, and we have to design bolt. So now the previous problem was we have one member and the loads were acting on that member, and we were interested in calculating stress at some other point, and we are interested in calculating or designing this pin, but load is not directly acting on pin, it is acting on some other members. We have to know how the load transfer is taking place from one particular member to another member. So in this case, if we analyze this, the force applied here, this particular interface will apply some load on the bolt in this direction, and because of this load, the some load will be applied here and some load will be applied here. If everything is symmetrical, we can assume that this load which is there on the interface, we can assume that this load is acting at the CG of this, means at the midpoint of this fork arm. And this is no doubt our assumption, and this assumption may vary from case to case, may vary from designer to designer, but with a proper justification that we'll be discussing in detail when we discuss about design of pen. But right now we can say either we can assume whatever load is acting on the interface like this, that this load is acting at the midpoint of this, or we can also assume that the load is acting in a triangular fashion. There is no load here and maximum load here, and the load in that case will, the CG will be like this. We have to, here we are assuming that the load is uniform at the interface. So these are the two cases, and uh, other thing that we have to understand, because of this load, the failure, it may crush this bolt or it may break this bolt like this. So there are two cases for the single load, that due to this load the crushing may also take place, and due to this load the failure of this particular bolt may also take place, and this bolt may uh, form in three part like this. So this is the top part, and that is the failed portion of this particular bolt. So it means this particular force which is acting in the plane of the cross section of failure, and this type of load we call it as shear load, that we have already discussed and learned in our uh, strength of material classes. The third case of design type of problem is related with this. Suppose we have this lever problem and we have to find out the what should be the dimension of this pin. That pin is shown here. So again, there is no direct load acting on the pin, but this pin is supported like this, and this complete member is also the complete assembly is shown with supported at point C and supported at point B. We know this is basically hinge support and this is pin support. So to find out or to design or to write down the left hand side of design equation, we have to where maximum stress is acting on the pin. So it means first of all we have to find out what should be the load on the pin. Unless until we find out the load, it is not possible to find out the stress. So for this particular case we have to find out the reactions at this support, and whatever reaction we get, the resultant of reactions will be the load on this pin. So it means now we have three different cases. In case number one, we need to know the effect of the load. In case number two, we need to know how the load transfer take place in assembly. And we also understood that a single load may induce multiple stresses, that crushing and shearing. And this multiple stresses means there are two modes of failure. This is another important term. We have to write down equation for each mode of failure. So design equation in this particular case, if we are trying to find out trying to design this bolt, we have to consider all possible modes of failure of the bolt. And in this case, we are clearly visualizing there are at least two modes of failure. There can be some more we'll be discussing later on, but two are quite obvious. One is crushing, another is shearing, in plane shearing. In third case, we need to find out the support reactions. So what does it mean? It means that we uh, have to first identify how to find out the effect of load at a point. Secondly, how to identify, how to view, how to find out the load transfer and identify the modes of failure. And thirdly, how to calculate support reactions. And no doubt the support reaction is calculated using the equations of static equilibrium and free body diagram, that also we'll be discussing in the next module. So these three left hand side related terms we'll be discussing in module 2, and in uh, the right hand side portion, that is the strength, calculation of strength, that will be discussing in next session. So thank you. Please like and share. Thank you.